Hi everyone, this is Avi and I'm making this video to share with you this paper, Statistical Analysis of Quiet Stance in 2D. And it's by Bakshi, Dizio and Lackner, and that's me. And I just want to share what's the small, most important nugget of information that has been worked out in this paper. So this paper studies quiet stance in like a person standing on two legs but in a rotating environment. Imagine like a platform which is rotating and a person is just standing in the middle and trying to stand quietly. Why do you even want to study that? Like, what's the big deal? What's like, we go to merry-go-rounds all the time, but why study this? The main motivation why anyone in the past has funded this project is because this whole line of project is that if humanity has to go into long distance space flight, if we go into space, there's no gravity, we lose our bone mass, basically. That's the problem, that's a major problem. And the only way we can handle that is by creating artificial gravity. And one of the ways we can create artificial gravity is to have a rotating spaceship, if not the whole spaceship, but a component of the spaceship is rotating, that creates radial centrifugal forces. And one can exploit that to kind of mimic gravity. But it comes with a problem. There is something called Coriolis forces. And the way to explain that would be, let's see. Here's an object. Suppose I throw, imagining something which is rotating this way. The axis of rotation is up, vertically up. And if I throw the object, Coriolis force acts perpendicular to the velocity of the object. It's something fictitious force, it's not really a real force. You can Wikipedia it and learn everything about it. So there's an issue, this Coriolis force deviates your trajectory. So we want to study what is the effect of Coriolis force on simple quiet stance. Now per se, if a person is just standing, you're not really moving, but nonetheless there is this little jiggling motion, like Brownian motion, ding 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 ding, your center of mass is constantly jiggling. So you want to see if Coriolis force at all affects that. And this paper shows that when you measure it with some stochastic measures, when you kind of do some analysis, which is explained here, cross correlation functions, and you do see that a person kind of learns to adapt to the environment even without knowing. The people do not have any idea that they are making changes because there is no per se pressure to make any changes. They can stand in the middle of the frame, whatever. Imagine a room is rotating. They're standing. There's no centrifugal forces acting on it, on them, because they're standing in the center. But nonetheless, they make some changes in like about a couple of minutes. You can track that. They make some changes in their balancing without realizing. Now, that was the main experiment, but the main idea in the paper is something else, which is why I want to share this. So what we did was we went ahead and tried to model this whole system, what a person is doing in a rotating room. And the way we did was basically kind of a trick, or so in the physics world, people study polymers. They study exhaustively, and they had a whole mathematics of polymers already in their world. We just took it and applied it here, and that's the fun part. So what is the mapping between a person standing in a rotating environment and a polymer? So here it is. Imagine a polymer, okay, a chain, okay, which has its own stiffness. Now imagine this polymer, we have kind of fixed it here. Somewhere you're holding it with a pincer or something. And imagine that you put this whole system, the polymer, and with one of its base fixed in a thermal bath, like a beaker of hot water. Just imagine, okay? Now polymers usually have charge. Imagine there's a charged particle on it. And now imagine you put it in a magnetic field. Now this is going wild. What has that got to do with your original problem, which is a person standing in a rotating room? So it turns out, and here's the main nugget, that a charged particle, the force that it experiences when it is moving in a magnetic field, looks very similar to the force that a moving body experiences when it is in a rotating environment. They both are cross product. So if you Google for Coriolis force and if you Google for Lorentz force and just try to compare, there's an upfront minus sign, one has charge variable in front, one has mass variable in front, but they look very similar. And now imagine this is a body, okay, it's standing and a body just jiggles, polymer jiggles. The foot of a person is fixed at the ground because they're standing, the foot is not moving, the rest of the body is moving. You also fix one of the point in the polymer, kind of mapping, yeah, similar maybe, yeah, let's try what, it's crazy, but let's try, go on. A charge on the polymer put in a magnetic field experiences a force, Lorentz force. And if you just Google about the force, its nature is almost the same as a mass in a rotating room. So there's like one-to-one mapping. So we were like, let's see what happens. So there are a bunch of predictions physicists made about what would happen if a polymer is charged polymer is in a magnetic field, blah, 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 what would happen. You just take those formulas and apply here. And the predictions they have is about this stochastic variable, some kind of correlation function, how they will change with time. What the correlation function is, basically, very quickly, I'll tell you, like, if the body is here now, the center of mass, what about like 10 milliseconds later, where it is? What about 20 milliseconds later, where it is? What about 50 milliseconds later, where it is? What is the prediction where it will be? So you make a statistics of that. And that's kind of a correlation on the basis of time. Like this many time later, if I'm here, where will I be? So that function has a kind of a power law. Power law means how it, as a function of time, how it increases, and one can kind of calculate the exponent of that power law completely theoretically, and we found that the same thing applies here. So the reason, one of the main reason I'm sharing this paper is that this kind of universality. We say when something in one world is completely similar to another world, the maths is same, and so everything else follows because the maths is same. The first equation, the dynamical equation is same, so everything follows. So if you want to see an example of that case, then can study this paper. So that will be it. Thank you for your time, and we'll keep it here.